In this video I'm going to go over the CCEA GCSE Chemistry 2018 Unit 2 paper, and this is a higher tier. Question 1 part A, you just have to recall the definition of hydrocarbon, and hydrocarbon is made up of two words combined, hydrogen and carbon. So the definition then is a substance that contains hydrogen and carbon only, and only is important. On to part 2. So we have to name the hydrocarbons B, D and F. So we'll take a look at B to start with, and we can see that it contains a carbon-carbon single bond. There are no double bonds here. So this here is an alkane. This is a saturated compound. It contains only carbon-carbon single bonds. There are two carbons, and when an organic molecule contains two carbons, it's based on F. And because this is an alkane, it's going to end in ANE. All alkanes will end in ANE. So that's ethane. Okay, we'll go on to D. You can see that D now contains a carbon-carbon double bond. So that's an alkene. And alkenes are unsaturated. That means they contain at least one carbon-carbon double bond. It's got two carbons, so again it's going to be based on eth, but this time it ends in ene to indicate that it's an alkene. Finally F, well again you can see that it contains a carbon-carbon double bond, so it must be an alkene. This time there are three carbons, so now it's going to be based on prop. That indicates three carbons. Because it's got a double bond, a carbon-carbon double bond, it's an alkene, so it ends in ene. So F is propene. Part 3 is asking us to write the molecular formula for hydrocarbon C. Well, the molecular formula is the actual number of atoms in a molecule. Remember, empirical formula is the simplest whole number ratio of atoms. If we have a look at C, there are three carbons. 2, 3. So I'm just going to put that down beside it. So C3. And then we'll count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So that's how many carbons and hydrogens there are in one molecule of C, which is propane. So the answer here is C3H8. And finally on this page, the complete combustion of hydrocarbon D. Well, when hydrocarbons burn, they produce carbon dioxide and water. So D is ethane. You can see it up here, which is C2H4. It's going to burn, react with oxygen, forms carbon dioxide and water. It obviously needs balanced. So we'll start with the carbons on the left. There are two carbons. That means we need two carbon dioxides over on the right to give us the two carbons on the right. Then look at the hydrogens. On the left there are 4, on the right there are 2. So we need to balance the hydrogens. We'll do that by putting a 2 there. The last thing we balance is the oxygen. If we look at the left, there are 2, and on the right hand side there are 6. So 2 2s are 4, plus the 2, that's 6. So we need 6 over here. And we achieve 6 by putting in a 3. So when you're balancing these equations, the combustion of hydrocarbons, start with the carbons, then do the hydrogens, and finish with the oxygens. To which homologous series does hydrocarbon A belong? Well, I've drawn hydrocarbon A to the right. We can see that it contains only carbon-carbon single bonds. It's an alkane. There are no other functional groups. Now, homologous series is like a family. So this here belongs to the alkane family, or the alkane homologous series. That's actually butane, because there are 4 carbons, and anything based on 4 carbons starts with but, and as it's an alkane, it ends in ane. The general formula then to which hydrocarbon F belongs. The general formula then of the homologous series to which hydrocarbon F belongs. Well, F, which I've drawn on the right, is an alkene because it's got a carbon-carbon double bond. We named it earlier as propene. So what is the general formula of alkenes? And this is where you have to be able to recall CnH2n. So in this example, there are 3 carbons. So N would equal 3. So if N equals 3, that means then we would have 6 hydrogens. And you can see that in this example of propane. There are 3 carbons and there are 1, 2, 3, 4, 5, 6 hydrogens. Part 7. Which hydrocarbons react with bromine water? Now, bromine water tests for alkenes. In other words, the carbon-carbon double bond, which we can see here. And bromine water is an orange colour. Pure bromine liquid is a red-brown colour, and bromine water is orange. And when it reacts with an alkene, it'll go from orange to colourless. Remember, you don't say clear. So what we're looking for then is which of the hydrocarbons contain a carbon-carbon double bond. You should be able to see the different hydrocarbons to the right. And remember, we're looking for hydrocarbons that contain that double bond, that carbon-carbon double bond. Well, A doesn't, B doesn't, C, no, D, yeah, there's a carbon-carbon double bond, and F also contains a carbon-carbon double bond. So D and F, when a hydrocarbon burns in an incomplete supply of oxygen, the products are carbon monoxide, you'll get water, and soot. There are 3 marks, see here, the soot, which is carbon. B, name the type of polymerization. So this is referring to D. So D is the alkene ethene, and alkenes, when they react to form a polymer, it's known as addition polymerization, where the small molecules, the monomers, join together to form a polymer. So part 2, the structural equation. Well, the structural equation requires you to put the alkene that we start off with, so this is the monomer, and we want to show that this here reacts with lots of other ethene molecules to form the polymer polyethene or polythene. Now it's like an equation, so we need an arrow, and when ethene joins with other ethene molecules, the double bond disappears. And we still have the hydrogens attached to those carbons, but we'll have to show that carbon has 4 bonds around it and that this molecule continues. So we've got to put bonds either side of those carbons. Now this here is the repeating unit. It's this unit which repeats over and over and over. So this goes inside brackets, and you've got to make sure that this bond goes through the bracket, and the same on the other side. Make sure the bond goes through the bracket. In any equation, or balanced symbol equation, we always have to balance it. So what you need to do then is put an N in front of the ethene in this case, and you do this for any structural equation for the formation of a polymer, so it doesn't matter what it is. So I'm putting an N, and that just represents any number, so it could be 1,000, 5,000, etc. And then on the right hand side, the N goes to the right of the repeating unit. The polymer formed from D, well, D was ethene. That's the monomer. So when you have lots of ethene monomers joining together, it forms the polymer. There's going to be polyethene. Or we normally just say polythene. That's okay. Two methods used to dispose of the polymers. Well, they can be put into landfill or they can be incinerated. So don't say burning them, it's actual incineration. Part C, hydrocarbon D can also react to form ethanol. Well, the ETH bit tells us there are two carbons. And alcohols, we know it's an alcohol because it ends in OL, contain an OH group. So one of the carbons has to have an OH group on it. Now it doesn't matter where you put it. I'm just going to put it on the end. So that's ethanol. The OH could have been down here, and then I could have moved the H up there. Or I could have swapped these two over and put the OH up here and moved that H there. It doesn't matter. For the OH, you could have shown the bond between them, between the O and the H. But we don't usually do that, we just normally write OH. When alcohols are warmed with acidified potassium dichromate, and this is an orange colour, the alcohols get oxidized and the potassium dichromate solution will change from orange to green. Question 2, at what time did the reaction finish? Well, that is where the line is horizontal. Now it still hasn't finished at this point, but it looks as though it is there because that line then stays horizontal all the way along. So it's here or here, and you'll be allowed either of those. So 250, 260, 270 to 275. And don't forget your units, and time here is in seconds. Now you're asked to draw a labelled diagram of the apparatus used to obtain the results. So I've put in the instructions that were given at the start of the question, and if we have a read through it, there was carried out the calcium carbonate with excess hydrochloric acid. It was carried out in a conical flask, and the measurements were taken every 25 seconds. Now on the y-axis, the label was mass of flask and contents in grams. So we have to weigh the conical flask. So that's going to need a balance, an electronic balance. So I'm going to draw the conical flask, and then we've got calcium carbonate in here. That's going to be sitting on a balance. Again, it doesn't have to be a really detailed diagram. In all rates experiments, measurements have to be taken at set times. So you've always then got to show a stopwatch or stop clock, some sort of timer. Now it does say labelled, that's just a given as well. Now you're told to do that, but you must always label diagrams. So we've got our conical flask, then we've got hydrochloric acid and the calcium carbonate. We have the electronic balance, and lastly the stopwatch, stop clock, timer. On to part B, explain that in terms of particles the effect of decreasing the temperature. So just be careful here, we're asked decreasing, often it's increasing. So here's going to be the opposite way around. So the effect of decreasing the temperature will be that the rate decreases. And the reason for that is that particles will have less energy, or you can say particles move more slowly. This will result in fewer successful collisions per unit time, and you must always finish explanations to do with rates with per unit time. You could say per second, per minute, or you could say there are less frequent successful collisions. On to question 4. There are some questions which were asked in the older papers and it's not in the new spec. And then also there are some questions that have been moved to Unit 1. So we're just going on to question 4. Explain how rust is prevented from forming in test tube 3. On test tube 3, the water has been boiled, so the dissolved air, the dissolved oxygen has been removed from it, and then the oil is put on top to stop the oxygen from re-entering. On to test tube 4 then. How is rust prevented? Well, it contains anhydrous calcium chloride, and this is a drying agent. So what it does is that it removes water. So there's no water or water vapour in the atmosphere inside that test tube. Part 3 suggests why more rust would eventually be formed in test tube 1 compared to test tube 2. Well, the difference between these two is that test tube 2 has a bung. So that means that it's going to have a limited supply of oxygen. In test tube 1, oxygen can keep coming in here, and obviously that's not the case. So there's some oxygen in here, but with that bung on, it prevents any more oxygen from entering. The chemical name for rust is hydrated iron 3 oxide, and then a barrier method is something like painting, metal coating, plastic coating, galvanizing, etc. Explain how magnesium is able to prevent iron from rusting. Now, this is a case of the reactivity of the magnesium and the iron, or the comparison between the two reactivities. Magnesium is higher in the reactivity series than iron. So when there's a competition between the two, the more reactive metal will react first. In this case, it's the magnesium. So here you have to say magnesium is more reactive than iron, or for that point you could say magnesium is higher in the reactivity series than iron. And then for the second mark, you put in magnesium reacts first. Then another metal which can be used in sacrificial protection, well, magnesium and zinc are very similar. So zinc is the other metal which could be used here. So C, explain why rusting is oxidation. We'll have to explain this in terms of electrons. Well, rust is hydrated iron 3 oxide. So if I put that in up here, iron 3 ions are what are in iron 3 oxide, and they are formed from iron. So the iron, when it rusts, loses electrons, and oxidation is loss of electrons. So that's the half equation. Now you could write that equation out, or you can explain that in words, but whichever way you do it, you must finish oxidation and reduction explanations with definitions of what oxidation and reduction are. So in this case, it's to do with oxidation. So we say oxidation is the loss of electrons. You can see the answer to D, part 1. In this part of the question, we have to explain why the reaction is exothermic. In other words, why does it give out heat overall? So what you've got to remember for this type of question is that when bonds are broken, and that's what happens to the reactants, the bonds between the sulfur and the oxygen and the carbon and the oxygen have to break. Atoms rearrange themselves to form sulfur, and then carbon and oxygen here to form carbon dioxide. So bond breaking requires energy. That's an endothermic process. Bond making is an exothermic process. Right, that gives out heat. Because this is an exothermic reaction overall, it means this side must be greater than this side. So the energy released when the bonds are made is greater than the energy required to break the bonds. Or another way of saying that is the energy required to break the bonds is less than the energy released when the bonds are made. And for this type of reaction, you also have to put in the names of the reactants and products. That's important. So we're saying the energy required to break the bonds, and we say where those bonds are broken. In sulfur dioxide and carbon monoxide, and I would just write in the chemical formula for those substances. I think it just makes it easier. So in sulfur dioxide and carbon monoxide is less than the energy produced when bonds are formed, and then we say where those bonds are formed. The bonds are formed in the products sulfur and carbon dioxide. And just to remind you again, you could say it the other way around. That is, the energy produced when the bonds are made in S and CO2 is greater than the energy required to break the bonds in SO2 and CO. So the key thing is to remember that energy is required to break the bonds, and that happens to the reactants. Energy is released when bonds are made, and that happens in the products. Number 5, a metal reacting with cold water gives the metal hydroxide and hydrogen. Calcium here has a valency of 2. Hydroxide has a valency of 1. I'm going to swap those over. And these are 2 different elements here, so we've got to put brackets around those. Observations. Well, hydrogen gas is given off, so you're going to see fizzing. The metal would disappear, so you could say that, or the calcium disappears, not just disappears on its own. Other things you could say are that the metal or the calcium sinks. Now, it does float as well. If you were to do this in the lab, you would see the metal floating to the surface. But that's because the bubbles of hydrogen gas give it buoyancy. So don't say it floats. Another thing would be that a milky solution or a cloudy solution forms. And a final one would be heat is produced, which is a very common observation in chemical reactions. Now, drawing this diagram can be tricky, so do make sure you practice this. So I'm going to draw a boiling tube that's going to contain the magnesium, and the damp mineral wool will have a delivery tube, and it's going to go into a beehive shelf. Now, I'll have a look at common mistakes after I finish the drawing. We need a bung in the boiling tube, and the delivery tube obviously goes through the bung. This needs to be set into a water trough. And then we need to collect the gas, because we're told here it has to be collected. So we're going to use a gas jar. You could use a boiling tube here. If you use a boiling tube, then it needs to look like a boiling tube. So water will be in the water trough, and it has to be above the beehive shelf. So it has to be above this height here. The gas jar itself is filled with water. We've got magnesium in the boiling tube, and then we've got our damp mineral wool. So that's the drawing of it, so now it has to be labelled. Now I'm going to show you common mistakes that people make. One is that they draw a line all the way through the delivery tube here. Now, when you draw this diagram, you've got to ask yourself, can the gas travel all the way through this apparatus into the gas jar? Well, as I've drawn it now, it can't, but you can see there it looks as though it would get blocked. So make sure you don't do that. You don't draw the line all the way through the delivery tube. Another common mistake is that people will draw the delivery tube going through the water trough. Obviously, you can't do that. It has to go in along the top of it. And then if we go in here Sometimes people just draw it like that. Again, that appears as though the gas would get blocked, or they might draw a line right across there so the gas then can't actually get up through the hole into the gas jar. So as a final common mistake is that people draw the water level in the water trough below the top of the beehive shelf. So just pay attention to that, folks, and make sure you don't make those mistakes. When magnesium reacts with steam, the solid formed is magnesium oxide. Remember, when magnesium or a metal reacts with water, you get the metal hydroxide formed. But when it's with steam, it's the magnesium or the metal oxide. And it's with steam because from the diagram, we're using damp mineral oil. So as it's heated, the water and the mineral oil evaporates, turns to steam, and then it passes over the hot magnesium. Okay, we're going on to question 6, part A. So I'm going to draw a diagram of what's happening here first. Diagrams can often help you see and understand what the question is about. So we dissolve 1.48 grams of the carbonate in 1,000 cubic centimeters, which is a cubic decimeter. So let's see if I draw it. And then 25.0 cubic centimeters of this solution were placed in a conical flask, as we were told here. So imagine that I take out 25.0. And that's of the metal carbonate solution. It is then titrated against hydrochloric acid. So the burette would be here. And it's 0.08, a molar solution of hydrochloric acid. And it takes 12.5 cubic centimeters to neutralize the metal carbonate solution. And then obviously we've got indicator in here. So let's see the first part. State the colour change. Well, methyl orange has been used. And the metal carbonate solution is alkaline. So the colour of methyl orange in an alkaline solution is yellow. And when it is neutral or just slightly acidic, it will go red. So the colour change here is yellow to red. Number of moles is concentration times volume over 1,000. Because we've got to convert the cubic centimetres into cubic decimeters. So we do that by dividing by 1,000. The concentration of the acid is 0.08. We're told that the volume is 12.5 over 1,000, and that's 0.001 moles. Part 3 then, use the balanced assembly equation to determine the number of moles of the M2CO3. Well, you can see it's a 2-to-1 ratio. That means that the number of moles of the M2CO3 is 0.0005. So just to go over that again, we've calculated that the number of moles of HCl required to neutralize the solution is 0.001. That means that they have reacted with 0.0005 moles of the M2CO3. Now the next part of the question, which will be in the next slide, asks us to calculate the number of moles in the 1,000 cubic centimetres. So we've worked out that there are 0.0005 moles in here and 25 cubic centimetres. But this was taken from the 1,000. So to go from here to here, we need to multiply by 40. So if there were 0.005 moles in here, then it's going to be 0.0005 times 40 in here. So this is the next question. It's going to be 0.0005 times 40. And this will give us the number of moles in the 1000 cubic centimetres. That's 0.02. So now we've got the number of moles. We know the original mass that was used. From the initial part of the question, that was 1.48 grams. Well, if we use N equals M over MR or over RFM, the mass was 1.48 and the moles is 0.02. So we were able to work out the formula mass of it just by rearranging the equation. So the RFM or the MR is going to be 1.48 divided by 0.02, and that's 74. So that's the mass of the M2CO3. Well, we can use the periodic table to work out the split. Carbonate is 60, so that's 12, and that is 16 times 3, which is equal to 48. So that means if we do 74 minus 60, that equals 14. So that equals M2. Therefore, 1M is going to be 7. And that is the mass, the relative atomic mass. So you go to your periodic table and find the element which has an atomic mass of 7, and you will see that that is lithium. Or you can give the name, it just says the identity, so you can give the name or the symbol. And part B, the number of moles of potassium hydroxide, which reacts with 0.00125 moles of sulfuric acid. Well, you can see it's a 1:2 ratio. So you're going to have twice the number of moles of potassium hydroxide. That equals 0.0025. Then work out the concentration. Well, concentration is equal to the moles over the volume. And we're using a volume of cubic centimetres here. So when you rearrange this equation to give us concentration, we need to remember to multiply this by 1,000. So I'm going to do 0.0025 over the volume, and you're told the volume here, it's 32 cubic centimetres, or 32.0. Then we multiply by 1,000. Remember, the 1,000 is there because of how we rearrange the equation to give us C. And that works out to be 0.078 moles per cubic decimetre. We then have to convert that to grams per cubic decimetre. Well, here we're going to use N equals mass over MR over RFM. So we have got the value in moles per cubic decimetre. And we can work out the RFM of potassium hydroxide. So it is KOH, and that equals 56. We want to work out the mass. So it's going to be the moles times RFM, which is 0.078 times 56. That gives us a value of 4.38 grams per cubic decimetre.